Welcome to our data science project, how to reduce uncertainty in the decision-making process for Yamaha in motors, by Team 158. Our business problem is how to reduce uncertainty in decision-making process for Yamaha in motor. Recent global events such as the pandemic, component shortages, and new international conflict generate a lot of speculation. It's necessary for the business to reduce risk in the decision-making process by using analytical models. We're gonna address this problem with the following strategy. Perform an exploratory data analysis of Yamaha motorcycle sales of the last 5 years, and then we propose 5 different approaches that help us make an educated estimation of the motorcycle sales in the next quarter. Let's start with the ARMA model. To identify the process, we first check whether Yamaha monthly sales from 2017 to 2022 is stationary. We do this by examining the sample autocorrelation function. If this function quickly tends to 0, then it is likely that this series is stationary. We validate this by performing an augmented Dickey-Fuller test, so this series turned out to be stationary. Next, use the sample autocorrelation function to infer the order of the moving average component, and the partial autocorrelation function to infer the order of the autoregressive component. Having found likely candidates for P and Q, we estimate the model and then conduct some basic diagnostic checks. A box-unit test is performed to validate the assumptions. So this is how ARMA 1-2 model fit look like. All coefficients are statistically significant and all white noise assumptions were met. We can see that it fits well. Finally, according to the ARMA 1-2 model, this is the final forecast for Colombia Yamaha sales for the next 6 months. Let's dive into the next model, that is linear regression. We start data cleaning process by removing, renaming columns, and dummies creation. Next, we run the train and test datasets. Then, we plot a heat map correlation. In the analysis part, we remove not statistically significant variables by looking at high p-values. Our R-squared is 36.6%. A weak linear correlation and archaic measurements are huge, so our model is highly complex. On top of that, we don't have normality and multicollinearity assumptions. We perform an ANOVA to verify that the selected variables are indeed not significant. Our final model results from running steps 2 and 5 until there are no independent variables left to be removed. We undo the dummies and run the prediction. However, this model is not reliable due to multicollinearity issues. Our next model is random forest. Analyzing the results obtained by individualizing each motorcycle model with their respective departments, the following is concluded. Due to the low and intermittent demand that is presented for a certain motorcycle model in certain departments of Colombia, many of these do not have enough data for training a model. Each motorcycle model has a different behavior and demand in each of the departments with respect to another motorcycle. That is, a motorcycle model may have a greater presence and higher sales in a department than another motorcycle model. A possible solution for the lack of training data could be the aggregation of departments with similar characteristics of sales in a single dataset for each motorcycle model, taking into account that the demand differs as explained before. Extreme gradient boosting, or XGBoost for short, refers to a class of ensemble machine learning algorithm. Ensembles are constructed from decision tree models. Trees are added one at a time to the ensemble and fit to correct the prediction errors made by prior models. It was selected for a problem since it is both computationally efficient and highly effective. These are the result of the training model for a specific department and motorcycle model. We have an estimated error of 16 motorcycles due to a month with high discrepancy. However, considering all the departments, the error is greatly reduced, becoming only 8 motorcycles of difference between predicted and target sale. Finally, we obtain a prediction for the next quarter, and it is an estimate of 32 motorcycles in each month for the same department and model reported before. Our final model is neural network regression. Normalizing the data allows the model to reach a better response in less time, optimizing the learning process. When training the model, it can be seen how throughout each epoch the data is being trained, but presenting difficulties with the validation data due to the complexity of the data or the lack of data in the training. The results obtained differ from those expected, but in an irrelevant magnitude, which gives an approximation of the acceptance of the model. The other hyperparameters should be checked further to find the most stable ones. For the deployment of the application, we use Azure Cloud, where we configure a virtual machine with Ubuntu. A version of Python 3 is running on a virtual environment, a SQLite database, and Streamlit. Now, let's talk about the app. The application is divided into sections to be able to navigate more intuitively. The first section is the home, where you can log in with your username and password. After the login, you will see the forecast through a map. Which can be modified using filters of department, month, or motorcycle model. There is also a comparative table between the implemented models. The second section is the sales history, where an HTML code is embedded from a Power BI report of the company to be part of this application. The third section corresponds to the description and information of the project. The fourth section will allow you to create new users to access the application. And finally, the section of the development team of this project, Team 158, who make all these projects possible. We can conclude that sales team, marketing team, and management team are gonna have a better intel to make decisions in their respective areas. Thanks for watching.